Today I'm going to talk about something both involving elliptic cohomology or topological modular forms and global categorical symmetry. So this is a joint work with Theo in this collaboration and another Dan Berwick-Evans from UIUC. And so I personally have been studying this kind of topic, elliptic cohomology or topological modular form in relation with supersymmetric quantum field theory. And this is actually the first time for me to do some work seriously involving those global categorical symmetry. So I'm really honored for this opportunity to present this work in this workshop. So let me start. So of course I'm interested in elliptic cohomology theory, especially topological modular form. And the important thing for me is that it is related to some classification of supersymmetric quantum field theory by the celebrated Segal, Stolz, Teichner proposals. So one of Stolz, Stefan here. That's also appreciated. So I'm not going so much in the detail about the Segal, Stolz, Teichner proposal in this talk. So I'm starting to talk about the topological modular form, look into that. And if you say topological modular form, it can mean three things. The first thing is called the TMF. And the second thing is called the TMF. And the third thing is called a TMF. So it's very difficult to pronounce. So please, yeah. So this joke is already made in front of some of the people, but so I think I'm allowed to do this in front of this big audience. So anyway, this is significantly different things mathematically, and the difference. In a pure mathematical sense, the difference is following. So TMF, large TMF, is about holomorphic weakly holomorphic modular forms. And in the modular stack language, so that it is in the definitionally, there is a definition you can just write in this way. Where here, this is the modular stack of elliptic curves. But the caution is that this thing is taking into account not the complex analytic modular form, elliptic curve, but elliptic curve over any rings. And also, in the most modern frame, so the formulation of topological modular form, it is better to talk in terms of spectral algebraic geometry. But anyway, so this may be a fancy object, but you can just take a complex point on that, and you recover the more familiar classical thing, which is a holomorphic, weakly holomorphic modular form. And this thing then going to be the usual familiar modular stack of elliptic curves over C. And you can represent it in terms of upper half space divided by SL to Z. And on the other hand, the difference is that this mixed TMF is about the compactification. So compactified moduli. So there is a canonical Dorien-Manifold compactification on this modular elliptic curve. And this amounts to adding the tau equals to this limit, adding this point. And it is important in this talk to do this coordinate transformation and represent this modular form in terms of the Q series. And in terms of this Q series, you are adding the Q equals to 0 point on the moduli. So that it, in the modular form, it affects, the effect is really simple, that the generic element in this ring is written in terms of this Q series, and the labeling is from, so I'm only allowing the finite pole, but you allow poles of finite order. But on the other hand, the holomorphic modular form, is about allowing no poles. So this seems to be very canonical thing to do. But one of the message I want to emphasize important in this talk is that actually this notion of the holomorphicity of modular form maybe can be regarded as non-canonical thing. I'm going to extend on it later. And what about the other thing? So actually, in today's talk, this version of the TMF is not playing a big role, so you can just forget about it. But just mention that this is a connective cover of this TMF, and it is of particular importance if you want to analyze TMF, for example, computationally in a homotopy theory. It is, of course, important thing, but there is no nice moduli description in this way, so that it is not going to be playing a particular important role in today's talk. So this is the purely homotopy theoretical definitional part of those topological modular forms. And what's important to relate to QFT is, of course, the Segal-Stolz Teichner. And for that, actually, there is really a good reason that Stolz-Teichner, Segal-Stolz Teichner is about this version of the modular form, topological modular form. So there is a nice interpretation and a highly expected fact that this version of the topological modular form classifies 2D 0,1 supersymmetric QFTs. And it is so if you look into that, it is obviously important to do this version of the TMF. On the other hand, in this viewpoint, it is a natural question to ask what the QFT interpretation of this thing. But it has been somewhat mysterious in this point of view. And also, the important recent development about the elliptic cohomology theory is the genuinely equivariant refinement of that. And there is also a nice story about equivariant refinement of the Stolz-Teichner picture, that this G-equivariant and equivariant twisted TMF corresponds to the putting the G-symmetry in QFT and the anomaly in G-symmetry. And the equivariant version of the TMF is constructed in a way that really that expectation, Segal-Stolz-Teichner expectation, is manifest. So because of that reason, partly because of that reason, there is no counterpart of the nice G-equivariant version of this version of the TMF. And this is a purely mathematical question to construct a nice theory of G-equivariant mixed TMF, which hasn't been developed. And so this is the topic of today's talk. So the big question, I said 2 points. So the first point, I repeat, is what is the QFT meaning of this mixed version of the TMF? Another question is a pure TMF theoretical question that do you have a nice theory of the G-equivariant mixed TMF? And another more speculative question is that can we put categorical symmetry in a Segal-Stolz-Teichner picture? So this means that, okay, so I started to talk about G-symmetry, and in this collaboration we learned that G-symmetry is not all the symmetry in QFT. So it is natural to think about put more non-invertible symmetry in this picture, and what is the equivariant TMF for such a category. And those kind of questions we eventually want to answer. And the goal of this work is to at least partially approach this answer. So I'm not saying that I'm giving an answer to all the questions, but at least partly approach that. So the particular result I'm talking about today consists of 2 things. The first thing is Yes-Go theorem. And the second thing is no-go theorem. And the yes-go theorem is to answer this part of the question, at least partly. So construct a version of the equivariant, G-equivariant mixed TMF. And the no-go theorem, on the other hand, is that this TMF turns out to be not having a string orientation, which is actually expected, naively expected to have for the topological modular form. So no-go theorem, to repeat, is to show that if you want to equivariantize this version of TMF, you cannot get a string orientation, sigma orientation, which is actually true for large TMF. So these are something which I want to present. And I want to emphasize that to get to these results, So to get to these results, it is very, very important to get an input from the BOA theory or modular tensor category. And what's the question?
Some years ago, with one of your other collaborators, we found some non-invertible symmetry for the monster CFT, which can be trivially viewed as the 0,1. Is that related to the third point?
So I think I'm not regarding that as a symmetry, but it's rather regarded as a particular element in the TMF, I think, in that point of view. So terminology or notation I ask you to remember in this 1 hour is this small MF means this holomorphic version of modular form, and this large MF means this weakly holomorphic version. And I want to really talk about the difference between. So is there any other question at this point? So let me move on. So the thing I want to talk about today is summarized in this diagram. So this diagram repeatedly appears in this talk. So I'm going to draw some colored arrow inside this diagram. So, but before doing that, let's look at the objects in this diagram. So these are what already have looked at. So the weakly holomorphic modular form, the module over that. So you can regard it as SL2Z module if you like. And this is a spectral topological enhancement of that. On the other hand, the thing on the outer square maybe look more familiar to you. So this is the category of unitary vertex operator superalgebra. And this is the unitary spin modular tensor category. And the plus sign, I'm going to introduce something, but let me ignore for a moment. So this is something about modular tensor category. And I want to in this talk, I'm assuming a niceness condition for BOA, like rationality or C2 cofiniteness, in order for taking the operation of representation category. So this functor works well. So I want a nice condition on which allows the representation category, irreducible modules, to be forming a MTC. So this is one of the arrow. And the thing in the upper half is that this is a collection of group with representation, orthogonal representation. So maybe more elementary thing. And on the other hand, this is the collection of G with level. Level is usually regarded as some element in H4, or more generally, something controlling the anomaly on the ISO M spin of degree 4. So there is a forget format in this direction. So you can, if you have a representation, then you can forget to the level corresponding to that Dinky index. And there is also, so even without talking about these modular forms, I can draw this map. And I'm not so much going into detail about this arrow, but this you can, if you are familiar with this kind of VOA, then maybe you can expect what I'm doing. So the fermion algebra divided by so the coset of G, or G fixed point if G is a finite group. And so this I'm going to explain later, but this construction factors through the level, if you remember only about the modular tensor category resulting in. So anyway, so this was the outer circle, outer square. And what I'm going to talk about is the relation between the modular objects. And I want to claim that there is a non-arrow in this way. I'm going to extend on it. And also there is a non-arrow. So let me just put on a word. So this non-arrow is called a vector valued modular form. And this arrow is, I'm going to explain later, also called a vector valued modular form. And on the other hand, this, let me just remark that upper side is about the spectral thing, and the lower side is about very purely complex analytic thing. And this square is very complex analytic. And on the other hand, if you forget about any lower side, I claim that there is a non-construction of G with representation sphere to put into the TMF module, which is the equivariant TMF. So, or ROG graded TMF. This is non-construction, as I said. And this is a whole of the non-construction, non-arrows. And I want to, based on that, to do something new in this talk. So what I'm going to construct in this talk in this work is this arrow. So this is a version of the equivariant mixed TMF I'm going to do. Yes?
What do the subscripts and superscripts in rep G mean?
Yeah, so this thing is, I can explain very well. So this is an orthogonal representation. And you know, the equivariant cohomology theory, you have to be the orthogonal representation to construct the representation sphere, first of all. And so this is very faithful. I'm eventually have to define, but this you can ignore for a moment. This is something technical. And so this is what I construct. And the point is that this is constructed in a way that this whole things commute. And on the other hand, the no-go theorem, or let me first do this. So what I expect eventually to do is to construct this arrow, which is some version of categorical symmetric TMF. And also, there is expected arrow. This is a mathematical point, which is a sigma-oriented mixed large TMF. But anyway, the point is that there is also obstruction arrow. So what I'm going to do by the no-go theorem is that this cannot factor like this. So this equivariant mixed TMF is, so this is can be regarded as some representation up to string oriented representation. So this is a restatement about the obstruction of the no-go theorem. And there is there is a corresponding statement in the lower side, and I can very easily explain, and I'm going to explain that this VVMF construction doesn't factor through this UMDC. So from yes.
Am I supposed
to take these arrows as literal arrows? Like, is the claim, so for example, this arrow from USMTC to mod MF, are you saying there's a canonical way to associate a modular?
Yes. I'm going to explain all the thing, but this is a canonical way. So in a word, it is a ST matrix coming from the MTC, and you construct a SL2Z module. So
but there's, I agree that you can construct an SL2Z representation, but there's generally many vector-valued modular forms that transform under that representation,
so
right?
it's, so it is very important to distinguish elements in the corresponding modular mod MF and the element in the mod MF itself. So the particular section, so you're supposed to be talking about the, so if you're given one of the SL2Z module, you can construct many the section over that. And I'm not going to, I'm not saying that there is a canonical choice of the section, but actually it is an important, so good point. That what I'm going to use is that from having a data of UVOA representing that category, you actually have a canonical section on that, which is a full character of that. Anyway, I'm saying too much. So this was the diagram I drew. And so this is the goal of the thing I'm going to present. So the plan of the talk is that first I explain the non-square together with non-no-go theorem, which which underlies the above construction, what actually result. And the second part is the yes-go, to explain the yes-go theorem, the idea of how to construct this arrow, mirroring the construction of the bottom. And the third, finally, I want to say about the no-go theorem, why it cannot be, cannot be the string-oriented. And so the actually, the plan of the rest of the talk is I'm planning to spend most of the time talking detail about this thing, this picture to learn, and tell briefly about the idea of the upper half. So, do you have any other question for this moment? Yeah. Yes.
Do I assume that they have n equals 1 SUSY structure?
No.
Or no? Okay.
No.
So this is like, I'm supposed to think of this as the left moving part of a n equals 0, 1 SQFT? Or?
Yes.
Okay.
In a sense, yes. So the, yes. Yeah. So I'm going to move on to the explanation of the maybe familiar part of the story. And first of all, I want to clarify, without necessarily talking about modular objects, clarify the difference of just having a modular form, MTC, and having a underlying VOA. So if you have a, for simplicity, I forget about the super thing. If you have a UMTC, the picture may be familiar to you is the following. So UMTC likely to, so it is tempting to say that it is about the 3D theory, 3D topological field theory, which is the Lisitzky-Turaev theory. But you know that actually this is a relative or anomalous QFT. And the anomaly is controlled by Klein-Yetter theory associated to this category. So this is the 3D, 4D picture happening in the QFT. And over the modular of elliptic curve, so modular of elliptic curve, it is about the torus. So evaluating of the torus over this picture, what you get is that, so if you only had the standalone 3D QFT, then you would get a vector bundle over that. But actually, if you have this 4D, this is going to be a projective vector bundle. And the projectivity is classified or controlled by a gerb, which is given by putting the 4D Klein-Yetter theory on the elliptic curves. And in the gerb language, this Lisitzky-Turaev theory is the module over that gerb, flat module. So what changes by having a VOA, underlying VOA, is the following. So the VOA, if you start to learn VOA from the beginning, then it is to be describing some 2D theory, chiral 2D QFT. And actually, this is not a standalone theory, but it is having associated with a canonical 3D TQFT, projectively topological QFT, which is, I would say, the Chan-Simons theory associated to this VOA. And the relation between this picture and this picture is that having a VOA actually trivializes the 4D Klein-Yetta theory. And you can regard this Lisichkin-Choraev 3D TQFT as a projectively topological, not precisely topological, but something assigning to things are finite dimensional, topological in that sense, Chan-Simons theory. So what happens over the elliptic curve, modular of elliptic curve, is that this gerb is trivialized. And then you can start to think of this projective vector bundle as a honest vector bundle. So this is what you get from the Chan-Simons theory 3D. And having a chiral boundary condition is that you get a holomorphic section, which is, so my name of this 2D theory is Wezmino-Witten V, and Wezmino-Witten section. So this is the picture. And I want to, so today's talk is to, one step is to convince you that this having a section is giving a, what I call the holomorphicity data for the modular forms, vector valued modular form. So this data is allowing us to say what is holomorphic or not, having a pole or not. Yes?
Bottom row, do you still have a integer level restriction, or can you move away from that?
Integer, so the, but this integer level is needed for the this representation. So I'm restricting to those integer level because of that.
Okay. All right.
Yes. Yeah. So it's actually so the in the point of view of the topological, so the how to say? So the Segal Stolz Teichner, it would be really unnecessary constraint to have the finiteness in the 3D. So you can, so if you are given a generic 3D QFT, then you should be generic. But no, sorry. TQFT-ness is needed to talk about. To first of all, making sense of 2D 0,1's boundary on that. So generically, 2D, in order to make sense of 2D 0,1 boundary, you have to have a, naively have to have the 3D n equals to 1 supersymmetric theory on the bulk. But what I'm secretly using is that TQFT can be tautologically regarded as a n equals to 1 QFT on the bulk, so you can start to talk about n 0,1's boundary on that. And if your bulk theory is not a TQFT, then without supersymmetry, I cannot make sense of the 2D 0,1 supersymmetric boundary on that. So it is not obvious to allow me to talk about the modular forms on that. But so let's discuss on that later. So this is, yes?
Normally when I see this Segal-Stolz-Teichner conjecture articulated, it's about 2D n equals 0, 1 SQFTs that are at most on the boundary of an invertible TQFT. But so is it correct that you're considering a kind of generalization of this where the bulk can now be non-invertible?
Yes, exactly.
And that corresponds to having to consider vector valued modular forms and
yes.
Thanks.
Yes. So yeah. So this was the QFT and the explanation of the difference between having a MTC and VOA. So let me go to actual explanation about how to talk about the holomorphicity of the modular objects. So warm-up question is the following. So I'm going to getting back to the original, so the first or second page of the slide. So the warm-up question is that why can we make sense of the holomorphic modular form? So I said that holomorphicity is just about the Q expansion. So the pole in Q. So from this point of view, maybe it sounds very canonical operation to do that. So this submodule is just put back so that this submodule looks like very canonical submodule of this MF, large MF. But I want to say that is this definition canonical? No. And what's happening here is that we are secretly choosing this embedding. Equivalently, I'm choosing a coordinate of Q near the cusp. And further, this is going to be equivalent to choosing this omega, so extension of the cotangent sheaf to this compactified moduli. So if you regard just this cotangent sheaf as a general line bundle over the elliptic curve, it is a question about how to extend a given line bundle over an open subset to the closed subset. And this is a priori a non-trivial question. And actually, there is non-triviality here. So the pick is a classification of the line bundle. So the omega here, cotangent sheaf is one of the objects here. And I'm thinking about the lifting problem to here. And actually, this is not injective. So there are choices to do. And particularly, so this component lives in one of the so Z component, and this is reducing to Z over 12 component. And indeed, what affects is that modular form, this version of the modular form is so that 12 periodic. But so 12 periodicity element is given by the determinant, modular, so the modular discriminant, which starts from Q plus blah, blah, blah. And because this is Q plus blah, 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 this, if you invert this thing, it starts from Q inverse plus blah, 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 and this lives in here, but this doesn't live in here. So because of that, the dividing this is an invalid operation, which gives us that this is not periodic. So this, in this way, the choice of this lifting is actually non-canonical. And since this is going to be important because I'm going to talk about the general vector bundle over this thing. So in view of that explanation, actually it is very natural to think of this as the following. So if you are given a vector bundle over this open moduli, then you can just talk about the section with so the pole controlled as a module over this large MF. So this is what I call the F-valued modular forms, weakly holomorphic modular forms. And this is also called so general thing which is represented by some vector bundle is called the vector valued modular forms. And the holomorphicity data for F, such a vector bundle, is just a choice of vector bundle over this compactified thing, larger thing, which with isomorphism after the restriction. So this is, then I can talk about this section over this compaxified thing, and this I would call the F-bar valued small mf, holomorphic modular form. So this is somehow a very abstract thing I can do. And but practically what's coming, so how you get the vector bundle over this kind of thing is from a SL2Z module. So the question is that how does it look like in terms of the SL2Z module, familiar with? And I cannot ask, so, sorry. So how to actually understand the holomorphicity data is the following. So I'm, I started from this open moduli, And compactification, and I'm using this push-out diagram that actually I'm adding, so the neighborhood of this cusp, so the cusp is looking like a disk in terms of Q variable, and in view of that, I'm filling out this 0. And this is a push-out diagram, so that just if you are already having a vector bundle here, and I want to extend to this thing, then I should just prepare prepare some vector bundle over field disk with an isomorphism over here. So this is just something formal. So I wanted to just say that the question is about filling happening in this familiar disk. And in terms of SL2Z module, it's what's happening is like this. So if you are given a SL2Z representation over some complex, so unitary representation, and the familiar presentation of the SL2Z is S and T matrix, and this thing associates the vector bundle. That's okay. And in view of that, if you are given this SL2Z module, the associated large MF is understood as a holomorphic function over the H, which is SL2Z equivariant. And in this presentation, the Terry's in the Terry's work, what's fundamental is that the holomorphicity data, in the sense that the extension over the compactified moduli is exactly the choice of this T matrix, so the exponential of the T matrix. So T matrix is generating a non-torsional element in the SL2Z, and I'm exponentiating, so this exponential. And actually, if you write in this way, maybe it's getting somewhat familiar to you. What? What? Superscript. So self-adjoint. Self-adjoint. So So this is maybe familiar. So what? How does this kind of data appears is the following. So I again come back to something involving MTC and VOA. So if you are given an MTC, unitary MTC, you get SL2Z, so S and T matrix. And I want to say that it is SL2Z module, but actually projective because of the reason of the 4D non-triviality. And precisely the projectivity is controlled by what is called a topological central charge, which is a Q number given by modulo determined modulo HZ. And this regarded as the projective SL2Z, giving a projective SL2Z module structure on this the K theory of this C actually dual. And on the other hand, having a VOA gives us an SL2Z module with a holomorphicity. Sorry, I forgot to say about this middle arrow. So here, now I can say what is this plus sign is. So the plus sign is our definition that MTC data plus a lift of this topological central charge modulo 24Z. Then you can trivialize this thing by modifying the definition of T tilde, and then you can talk about really honest SL2Z module. So this is one step. And VOA, on the other hand, has more data. So VOA representation, actually VOA, if you have a VOA, you can talk about the central charge as a Q number. And so this in particular gives a MTC plus. so that you get you've got the SL2Z module. And another point is that if you are really given a BOA underlying that, so T matrix is generally a diagonal matrix coming. So the diagonal entry is given by each simples the self-braiding on that. And this is actually given an BOA, then you can make sense of the conformal dimension of each irreducible representation, which is the starting coefficient of the character of this associated irreducible representation. And you can, so this exponentiates to this theta, topological central charge. So this in particular gives a canonical exponential to this T matrix, which in view of this claim gives the holomorphicity data of the associated SL2Z module. So you can, from the data of BOA, you can canonically talk about what the holomorphic modular form is. Is it clear at this point? So what I explained so far is exactly this square. So I was not talking about super, so let's forget about it. But I just explained that there is an arrow, which I call the vector valued modular form. So gives the SL2Z module. And having an underlying BOA means that I can talk about what is a holomorphic modular form inside that, which I would define the small mf. So this is the square. And another, actually it is important for my purpose to give another interpretation for this small VVMF. Another characterization is available. And this comes back to your comment. So there is a Juice theorem. So the way how originally BOA, so the SL2Z module, vector valued modular form, blah, 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 appeared in the literature of the BOA is, I think, the following. So the Juice theorem, classical Juice theorem says that if you have a BOA, first of all, the collection of the irreducible character of representation, so the irreducible representation, you can think of some vector, and then it performs as a vector valued modular form. And in this, in our terminology, it means that the full character gives an element in the large MF rep A associated to the representation category of BOA. Here, this full character is precisely that if you are if you are given a representation, irreducible representation, so any representation you can take a character for that, and this is the trace of this Virasoro the action. And the full character is given by this vector valued modular form, which is the list of the full character for each irreducible modules listed in a way that it is so labeling is given by the irreducible modules, list of irreducible modules. And it is turned out to be a SL2Z invariant section, which gives an element here. And the claim is that by construction of this thing, what I defined as this holomorphicity data coming from this exponential is exactly saying that this MF is a minimal choice of the holomorphicity data, which accommodates this full character of BOA. Does it make sense? So I want to make a message that the message to gain is that BOA gives us a canonical particular section over these modular forms, vector valued modular form, and I'm defining this holomorphicity data to be the one that accommodates. So this is going to be holomorphic, and the minimal choice of that. Yes.
So I think I probably just missed it, but this MF lambda, is it like the space of holomorphic modular forms whose poles are sort of no more singular than lambda or something like this?
Yes, exactly. So that's a very good point. I didn't write it, but it is what you exactly said. If you are given a generic element here and ask for it is a holomorphic with respect to the lambda, you can just expand it and see the first pole order and look for if it is exceeding this or not. This is numerical. And this was another explanation of this. And I want to learn from it to construct, sorry about that. So I have to first say the no-go theorem in this context. And actually, this is no-do theorem. So very weaker version of this no-go theorem. So the no-go theorem would say that I obstruct any other thinking about any other reasonable construction, and I obstruct actually you don't get any reasonable map from here to here. But I'm just do the weaker version on that, which is that my construction of this VVMF doesn't factor through UMTC, and this is very easy to do. Just asking that. Okay, find two Theo VOA, which is whose underlying representation category is equivalent as a UMTC, but this exponential data is different. And so the conformal dimension is different. List of the conformal dimension is different. And this is very easy to find. And so this I want to mirror to this spectral story. So from now on, I'm going to explain the upper side of this, what we do and what we obstruct. So first I want to talk about the yes-go theorem, how to construct, or I'm not going to the detail, but the idea of the construction. So as I said, there is a non-arrow which is given. Sorry. This should be the large TMF. Sorry, non-thing is large TMF, equivariant TMF, and one to construct thing is this. Okay, yes-go theorem is the following. So there is non-arrow actually goes to the graded, so the virtual representation, but one point is that I have to start from the representation, having a representation which is not virtual. And I would call it as a rep graded TMF. And somehow putting a secret thing. And what to learn is, as I said, that if you have this VOA, then actually I'm getting a canonical section over this MF. Large MF, and this, in other words, given a pointed object in the mode MF. And I'm choosing a minimal choice, that this minimal choice of this thing, mode small MF, which accommodates this given pointing. This is one definition. And I learn from this definition and look for what is canonical section, what produces us a canonical section. And an answer is that if you are given a representation, honest representation, I'm having a Euler class. This is a canonical element in the ROG graded TMF. And for having a Euler class, you actually have to start from the rep, so the genuine representation, which is not virtual. And so what I want to do is that I want to define this thing, TMF module, to be the minimal choice of what accommodates this Euler class. And this is the idea. And why suddenly started to talk about Euler class is verified from the fact that if you're, so I said that there is a nice arrow going for B divided by G, and I'm using the fact that the Euler class gives the character for this for B divided by G. Yes, in this case. And actually, strategy, mathematically, how I do this is to use the, so what I wrote before. So I wrote some complex analytic moduli, description of the moduli, and actually the pole, so the neighborhood of the cusp singularity looks like this. And actually, the similar thing happens here. I'm lucky enough that the neighborhood of this compactified elliptic moduli, even though I'm doing some fancy thing like spectral algebraic thing, it is the formal neighborhood is looking rather familiar. This is a K-theory, essentially the K-theory with formal power series. This is a case, so the elliptic cohomology associated to theta curves. And I know this construction, and I want this construction. So this means that I just need to construct this with commutativity data on that. And we actually do this by really do the Fredholm operator, Dirac, so the Hilbert space and Fredholm operator, learning from those VOA, what's happening in the so the Majorana fermion Fock space VOA. And this is a rough strategy I'm following. So this was the very, very rough outline of the strategy. And now, finally, I want to explain a bit about the no-go theorem I'm going to do. The obstruction to string orientation. So first, I want to explain why I'm expecting string orientation to have for this side of the story. So the string orientation, if you, I have this very clear explanation in terms of VOA and MTC. So I claim that, or very well known that if you have two representations, and if you're B, so two representations, so the construction of per B divided by G produces generically different thing. But if your B and W has the same level, then the resulting UMTC is equivalent. Although this for B, so the underlying VOA is different. So this is the, yeah, so you can think of it as like the affine the algebra is only remembering the information of the levels, and this B and W are giving a free field realization on that, which produces the equivalent thing. And there are a lot of examples I can say about such pair. So this is 3, 4, 5. And okay, so in view of TMF, there is very established string orientation with physical interpretation. So the Andor-Hopkins-Letz orientation is about the non-equivariant version. And actually, non-equivariant version of all the TMF is string-oriented. So there is a nice map, and the composition is also have a nice interpretation in terms of Segal, Stolz, Teichner, that this construction saying that if you have a string manifold, you can construct a TMF element. And this is the sigma model, n equals to 0, sigma model. And the string structure is the anomaly cancellation needed for that. And so I'm saying this. And also a bit subtle status, but genuinely equivariant TMF is highly expected to be string oriented and established for those kinds of things. And on the other hand, the no-go theorem is saying that somehow this large TMF cannot be, so the equivariant mixed TMF cannot be string oriented in a sense that you have this isomorphism for string oriented difference. And so I could do the no-do theorem very easily. No-do theorem means that I prepared some construction and it doesn't satisfy the string orientation. But it's likely that I'm doing something. So this was my mistake. But actually, we are obstructing is that there is no reasonable choice on that. Choice to do that. And so the restriction is that, of course, I want to recover the large known TMF, so genuinely equivariant TMF. And another input, actually important, is that if you do the U1 version, U1 equivariant TMF, you want to recover the weak Jacobi form, at least for higher homotopy. And so this is I think reasonable assumption, and this is also true for our construction. And I didn't put, but so that I will, of course, impose that functoriality in the group variable. And from that condition, I can obstruct the string orientation in a fairly easy way. By the way, this Jacobi form, so because of that, there is a nice notion of TMF is U1 equivariant, which recovers topological Jacobi form. And this is coinciding with. Okay, so this is what I wanted to say. So the summary and the outlook is summarized in this picture. Okay, I did this construction and I obstructed this and nice diagram, and I want to complete this. And this is the topic I'm poking around people, also including Tomar. And so that this would be that categorical symmetric TMF, which I really want to explore. Thank you very much.